Hey, this is Stives with Beard Logic, and this is episode 2 in our series where we build an adventure game. I'd like to take a minute to thank those who liked, commented, or subscribed from last video. I wasn't sure how the series was going to be received, but because of you, I will be continuing it. With all that said, let's jump back into it. We left off last time in the middle of polishing the jump, so we can continue from there. As you can see, we've got the jump working quite well. And physically speaking, it is accurate, but you may notice it doesn't feel the same as jumps we've gotten used to in other games. So to make this feel a little better, we're going to increase the downward acceleration when the character is falling. Let's start off by adding a parameter so we can adjust the acceleration downward as we see fit. We already know if the character's in the air, so all we have to do is check the vertical velocity. So just include the additional acceleration when the velocity is less than 0. So let's check it out, and as you can see, it feels a little better already. Feel free to mess with this parameter to get the feel that you're looking for. I found 15 to be a pretty good value here. Alright, we keep adding more and more parameters. I think it's time we need to do a bit of a cleanup at the top, so let's add some headers so it's easier to see what the parameters are in the Unity editor. I just like using the header so I can see what parameters apply to what, and then I actually like to add regions around them too, so that I can simplify my code even further. This may seem like a bit of a trivial step, but ultimately it saves you time in the long run. Alright, we're going to improve the jump a little bit more here. We're going to add a bit of a delay before the jump happens. It's going to make the jump feel quite a bit more powerful. Alright, back to the update jump function. We're just going to check to see if that build-up time is above 0. And I just realized I'm going to be changing the velocity, so this is a really good place to comment up above so I remind myself what exactly this is going to be doing. So while we're building up, the velocity is going to be 0. So I scratched the build time. I think we're just going to check directly if the key is down. While the key is being held down, we're going to just add to the jump build time. That is, if the character's on the ground. Then we're going to initiate the jump when the player releases the key. The main idea here is just to try and get it working so I can see what it's going to do. And remember to reset the jump build time so it doesn't continuously build between jumps. So let's test this out. As you can see, holding down the key now does what I want, but allowing the user to hold it down for as long as they want sort of defeats the purpose of the effect. So let's add a new jump parameter called maximum build-up time. The idea here is that if the player has been holding the jump button for too long, we want the character to jump anyway. So some of you may have noticed that we weren't actually using the jump build-up time before. So yeah, this is where we're going to be using it. If the build-up time is greater than the max build-up time, then we fire the jump anyway. Just one more thing before we test this out. I want to change the jump speed into a range, so the amount of time that you hold the jump button will determine how much jump speed you're going to get. So instead of jump speed, we're going to have a maximum jump speed and a minimum jump speed. From here, we're going to use something called a linear interpolation. It's something built into Unity, so don't worry too much about the fancy names. Basically, if you consider the min jump speed and the max jump speed to be on a line, the linear interpolation will smoothly transition between the two based on the alpha that you provide it. The alpha value goes from 0 to 1. At 0, it'll be at the min jump speed, and at 1, it'll be at the max jump speed. You can consider it something like a percentage, but instead of going from 0 to 100%, it goes from 0 to 1. Fortunately, we have all the variables we need to get this to work. If we take the jump build time and divide it by the maximum build time, it's going to range from 0 to 1 just like we want. But we don't want it to go over 1, so we're just going to clamp it so that that doesn't happen. So let's check out what we've done here. Alright, so now if you hold the button, you're going to jump higher. But now if the button's held for too long, it's going to jump anyway. That said, you may have noticed a bit of a problem. We can continuously jump forever. Additionally, if you try and jump directionally after you've hit the jump button, it doesn't work. So let's quickly fix these problems. The first of which can be fixed simply by making sure that we're on the ground before we allow a jump. Now we're already handling that when the button is held down, but we don't handle it when the button is released. So we're always going to get the minimum jump when we hit the button in the air. So an easy way to handle this is just to make sure that none of this gets called unless the character is grounded. And there you go, you can't jump up forever anymore. But the other issue still remains, so let's see what we can do about that. So to solve this problem, we're going to add another member variable, and we're going to call it input, and then we're just going to replace the input direction with this variable. This is so that we have access to the input direction in our jump function. So now when we jump, we're going to initialize the velocity with input instead of adding to the current velocity. No need to modify the original velocity line there at the bottom. I made a mistake, so I'm going to be correcting it here in a second. The end result should look something like this. And there we have it. We've got the jump working just the way we want it. Now if you hold the jump button down for the maximum time, you get one heck of a jump. So I think we're going to modify a few of the parameters here just to make it feel a little better. What feels best is up to interpretation, so play with these parameters until you feel like you've got what you want. Alright, that feels much better. Some of you who have been following along may notice we're actually going quite a bit faster when we go on an angle. That's because when we're checking input, we're just adding the values together, and we're not doing anything about the result. All we have to do to fix that is to normalize the input. Let me see if I can explain that a little better. The two green arrows refer to just hitting a single key alone. Their length is 1, or the same as the radius of the circle. But if you were to hit both of them together, you end up with the red arrow. And if you look at the circle, you can tell that the red arrow is longer than the green ones. So when you normalize, it's just shrinking the vector down to a length of 1. Now I'm sure a number of you are thinking, oh, we're halfway through the video and we haven't even adjusted the wall jump. Not to worry though, we're going to be moving on to that right away here. So just like the normal jump needs to know if you're on the ground, the wall jump needs to know if you're against a wall. So we're going to create a function that allows us to check exactly that. As per usual, we're going to try and get this thing up and running as quickly as possible. So we're just going to cast a ray in the direction that the character is facing. One big problem with this approach is that you're going to have to be facing the wall pretty well directly on in order to get the jump to work. That said, we can get that sorted out later on, so let's continue. Now most of this code should be pretty familiar to you at this point. It's going to be fairly similar to the isOnGround function, with a few modifications. For those modifications, we're going to need a couple more parameters up top in the physics section. The first of which is a reference to the capsule collider, which we'll be using to get the radius of the player. And the other one is a float parameter, which I'm going to call the wall slide threshold. It's going to be used to determine how far away from the wall you're going to have to be before you're interacting with it. So the only difference between this raycast and the other one is that we're going to be using a very specific distance as opposed to just some random 0.1 value. The reason being is the radius of the player actually comes into effect here, whereas before, when we were casting a ray, it's starting directly at the player's feet, which is already perfectly at the ground level. So instead of some random value, what we're going to do is we're going to take the radius and we're going to add that slide threshold to it, and that will be our distance. Another potential problem here is if we're running up a ramp, it's going to think we're hitting a wall. In order to prevent that, we're just going to make sure that the wall's normal is not pointing upward. So for that, we're going to be using a dot product. It basically just takes two vectors and determines how closely their directions match with one another. For instance, if both vectors are normalized and they're both heading in the same direction, the dot product will give you a value of 1. Alternatively, if they're heading in the opposite directions, they'll give you a value of -1. So if we take the dot product between the global up vector and the ground, which generally points upward as well, we would have a value of 1. If we then took the dot product of a global up vector and your standard wall, we'd actually have a dot product of 0. So with that in mind, we can pretty safely say that we want the value to be somewhere between 0 and 1, so let's just set it at 0.5 for now. So for now, we'll just consider any dot product that results in a value below 0.5 as a wall. So because there's no real reason to cast this ray more than once per physics update, I think we're going to do the same thing that we did for the isOnGround. We're going to have an isAgainstWall as well. And we're just going to update that parameter at the same time we update isOnGround. So now we need to create a function similar to the updateJump function that updates when the character is against the wall. Let's call it updateWallSlide. Let's start off by assuming that if you're on the ground, you're not going to be updating as if you were against a wall. Then we just need to check to see if we're against a wall, and if we are, we'll slow the fall speed. This should give the player a little more time to perform the wall jump. So for this, we're going to need to add another parameter. We're going to call it something like wallSlideSlow. Now I'll likely have to tweak this value once we get into the editor, but for now we'll just set it at half gravity. And we just want to make sure that we're against the wall, as I was saying before. Okay, just a few more things before we test this out. One of which is, well, we haven't actually rotated the character yet. And seeing as we're using the front of the character as a determination of whether against a wall or not, we'd better do that. So it's pretty simple. Basically, I'm going to check the direction of the current velocity and have the player to face in that direction. We do want to keep the character up straight though, so we're going to remove the y value from the direction. One more thing I should mention is that if the new direction is 0, then we don't want to look in that direction because that's going to cause some issues. With that in mind, we're just going to check the magnitude of the new direction and make sure that it's greater than 0, or some small number. Now let's just make sure our script is referencing the capsule collider. Alright, finally after all that, let's test this thing out. As I mentioned before, I'd likely need to adjust the wall slide slow in order to get this to work correctly, so let's play with that right now. Let's first try double the gravity. Alright, well, I'd say that's working pretty good. We're going to want something lower than that, but we can definitely see that it's working. So after a little while of playing with these values, I realized that there was something weird going on. Ultimately, I realized that the additional fall acceleration was affecting this as well, so I needed to go back into the code to change that. Just a simple check to make sure that if we're against a wall, we don't add the additional fall acceleration. And with that small change, I think we've got it working. I'll just have to try it out one more time and see. Yeah, that's looking pretty good. Alright, one small correction from the last video is we need to make sure that the input is in update and not in fixed update. If you leave it in fixed update, it works, but you may notice some input being missed. You don't want somebody playing your game and trying to jump when they should be able to jump and not able to do so because of some weird input bug. Most of this is pretty straightforward, but we are going to have to do some modifications to get the jump to work correctly. One of the things we need to do is add a member variable to store whether the key is pressed or not. For now, let's just call it jump requested, and we're going to check that in the update function so that we'll be able to tell if the key is being held down anywhere else in this class. Actually, I think this might make a little more sense if we call this something like jump key is down. Then we can replace the input get key down here, and we're going to have to do something a little different for the next part. The reason being is that get key up detects when the key is released, which is not quite the same thing as when the key is not being held down. Though I think we can get this to be nearly the same as get key up if we just make sure that the jump build time is greater than 0. And one more quick change before we switch back to test it. In update jump, we're just going to allow a jump if we're against a wall and see what that does for us. So movement's working, and we should be able to get some sort of jump out of this. It looks like we can only jump if we actually choose the direction. Not bad, really, but I think we're going to take it one step further. So in the jump function, when we're about to jump, we're just going to check to see if we're against a wall. And we use the opposite of the character's forward direction to determine the movement direction instead of the input. For those who can't see, there's a negative sign in front of the transform.forward, which actually gives you the opposite direction of the character's forward vector. Alright, on to the final test of the video. Let's check this out. As you can see, we're sliding okay, and we're jumping just as well. And as I was saying, this is where we're going to be wrapping up the video. I think we managed to do quite a bit here. Next video, I plan on creating a rudimentary state machine so that we can determine which state the character's in, because once we have that up and running, it won't be that difficult to add animations to this. Anyway, time to wrap this up. If you have any questions or suggestions, let me know in the comments section. If you like this video or like where this series is going, please leave a like, subscribe to my channel, or share this video, all of which really help me out and encourage me to make more content. Thanks again for your support. Until next time, bye for now.